with distinguished invited speakers that are to review the current status and recent advance of this fascinating topic of dark matter and its relation with high energy physics. We have 5 distinguished invited speakers, and I want to thank the organizers. The organizers are Miriam Mondragon, Estela Garcés, Catalina Espinosa, and Eric Vasquez. Yeah? Thank you very much. And I want to mention that this is part of a program that we are initiating in this Institute of Physics. This is called the research programs of the Institute of Physics. And the aim of this research program is to further boost the scope of the research that we carry out in this institute. And then I'm really very grateful. And I will mention the speakers. This is Xerxes Tata, that he's going to talk about beyond the standard model. Priscilla Cushman, that she's going to talk about WIMP's direct detection. Alejandro Ibarra, indirect dark matter. Pierre Kibi, he's going to talk about action dark matter. And Jesus Zavala Franco, he's going to talk about the perspective of astrophysics in dark matter. They are all, okay? Did I miss someone? No, okay. Well, thank you very much, and we can start this meeting. Thank you. Please.
So thank you, Manuel, and thank you all the speakers. Our first lecturer is Professor Xerxes Tata from the University of Honolulu, and he's going to give us an overview of beyond the standard model physics based on basically supersymmetry, which has one of the most promising candidates for dark matter. So feel free, I think we have time for questions, and we'll have discussion sessions, but if you have pressing questions, don't worry, ask the speakers. The point of this workshop is to initiate collaborations and to help our students, young postdocs, and all people working here to get in touch with the latest advances. So take advantage that we have some experts here and make use of that, please.
Okay. Thank you very much. It's a pleasure to be here. I was in Mexico 25 years ago in the other side of the city, so this is a new experience for me. And anyway, I forgot everything that happened then. So I was charged to talk about beyond the standard model. It's a very vast subject. So as you can see from here, I will start by saying why we should go beyond the standard model and what there could be. But after that, instead of trying to do a very broad brush review, which will be just propaganda, I will focus on supersymmetry in these lectures. But I will keep going every once in a while to say, hey, the same thing will happen, or similar things will happen in other areas of beyond the standard model. Maybe this will become clear as we go along. So today I hope I will be able to talk about the basics of supersymmetry, and then we'll do some basics of supersymmetry phenomenology in lecture 2. And then after that, depending on time, we will talk about more modern things. So I hope this is what the organizers wanted, but we'll find out. So what I will not talk about, as I said, I will mostly be limiting the scope to supersymmetry. And even there, they will be sketchy because 2 hours is very little. And this slide was inspired by one of my colleagues who asked me whether I was going to do certain things. So I will tell you what I'm not going to do. Even though this is a dark matter workshop, most of my talk will not be about dark matter. And because I think you will hear a lot about dark matter from other people, but I will mention dark matter in other places. So let's start. Oops. So the standard model, Why? I wonder why this header came. Okay, I don't know. It's not going away. Okay, so the success of the standard model, we all know it has worked very well, and it led to rampant theoretical speculation over the last 30 years. I mean, a fantastic idea was grand unification, where in terms of one coupling, we tried to explain the strengths of the strong, weak, and electromagnetic interactions. And that required an amazing extrapolation over 13 orders of magnitude, something which can only be called Harvard chutzpah to do this. And if the idea had been correct, then when the gauge couplings were finally measured at LEP, and of course in 1989, it did not seem to work in the standard model. If it had worked, then the measured values of gauge coupling at LEP, which was at say around 100 GeV scale, you can extrapolate using the renormalization group equations of the standard model, and they would have unified, but they did not seem to. Initially, for the old people, the error bars were so big that it was okay, but the precision measurements didn't make it. So that was, then the question could be, are there extensions of the standard model in which they would unify? An experimental thing was, we have observed dark matter and neutrino masses, and neither of those seem to fit within the standard model. But from the perspective of today's lecture, this is the most important point. The standard model has an elementary scalar in it, and if you try to embed the standard model into a theory with the high scale, like a grand unified theory, then there are runaway corrections which we will talk about in some detail. And today we know that the standard model exists. So what do I mean by this? So the mass of the Higgs boson, the physical mass of a scalar, usually people say is quadratically divergent. And in terms of a cutoff, you will get some expression like this. This is the Lagrangian term, and then this is the quadratically divergent term if lambda were to be treated as a cutoff. But of course nothing, cutoff is an artificial thing. The more important thing is, if you embed the standard model in a gut, then there is a grand unification scale, and then this cutoff effectively gets replaced by the grand unification scale. Okay? So this grand unification scale in the standard model is a big number. It's like 10 to the 15 GeV. So you get 10 to the 15 GeV square here divided by 16 pi square is 100 or something. So 10 raised to 28 out here. Of course, you can take this to be minus 10 to the 28 and get this number to be 100 GeV square. But that is an awful adjustment of parameters. Again, I emphasize that this lambda is not a regulator, it is not a cutoff, but it is a physical mass scale. How large could lambda be? Logically, it can be anything because standard model is a renormalizable theory. But if you don't want the incredible cancellations that we just talked about, 10 raised to 30 minus 10 raised to 30 giving you 10 to the 4, then lambda cannot be too large. Lambda then has to be of the order of 1,000 GeV if you don't want these enormous cancellations. And this is, of course, a soft statement. You don't take it very seriously. Exactly 1,000 GeV, 2,000, 3,000, 5,000, 500, all are the same at this level. And what this means, if this argument is correct, that there must be physical new degrees of freedom with a mass scale which is of the order of lambda, around 1,000 GeV. Now, of course, this is not completely watertight. You should say here you're using a perturbative argument. So there have to be these degrees of freedom if perturbation theory holds or perturbation theory does not hold. That is the logical way out. So what can the possibilities of this new degrees of freedom that we talked about be? One idea was that you eliminate the elementary scalar, because this thing happened because there was an elementary scalar in the theory. And that used to go under the name of technicolor, and there were new particles with the technicolor interaction which were posited at that scale. Okay? And of course, this did not work. I mean, it worked very well for giving W and Z masses. It did not work as well for the fermion masses, we had to have something called extended Technicolor. But it all hung together, and because there were these new bound states, perturbation theory did not work. So that was the loophole we talked about. But of course, today we know that we have seen the Higgs boson, so this idea is not very favored. Another idea that was there was that gravity becomes strong not at the Planck scale, but at a very low scale, near the TeV scale. And if gravity becomes strong, again there are strong interactions at the TeV scale, and there would be degrees of freedom associated with that, and these led with extraspatial dimensions, and there would be the excitations in this extra compactified dimension. A third possibility would be to say what I call postponder problem. So you arrange the theory so that this lambda square term, which was there here, the 16 pi square came because of a one loop factor. If you can arrange things so that this term, quadratic divergence, only comes at two loops, you would get square of 16 pi square. So you could make lambda larger by one order of magnitude. And there were models like that. But then again, the problem would show up at the higher loop level, but it is not a phenomenological problem because LHC would not see things. If lambda were postponed to 10 TeV, you would be safe from LHC. But of course, we would then need a complete theory. Another argument which is disfavored now is there are strong interactions of the W boson. Somehow there would be new form factors or something coming in, but we know that is not the case because we have seen the Higgs boson. Alternatively, we could say that the Higgs boson mass is fine-tuned. Live with it. And then we would have this horrible word which we won't go into in these lectures. Or we could do a very old-fashioned thing and just try to invent a symmetry which controls the Higgs boson mass in the same sense that chiral symmetry, gauge symmetry controls the photon mass. The photon mass is zero because of a symmetry, gauge invariance, local gauge invariance. Or the fermion mass can be small because of the chiral symmetries of the fermions. And luckily, there is such a symmetry, and that is called supersymmetry. Okay? Supersymmetry stabilizes the mass of the Higgs boson so that you don't get this awful lambda square term that we had, and then our problem is ameliorated. If that is the case, then the new particles of supersymmetry would be the degrees of freedom which have to exist at that scale lambda. And lambda would have to be around a TeV. So these are called super partners. We'll talk about them in more detail. Okay? And the fact that they have to exist at the TeV scale gave us hope that when a super collider like the LHC starts taking data, these things will be produced. Of course, you know the answer is they haven't been produced, and we have to discuss whether that's, of course it's not a good thing, but we have to discuss whether it is a disaster, as some people have suggested. Supersymmetry is a weakly coupled theory all the way out, and it decouples very fast. The superpartners decouple very fast, which explains why the precision measurements at LEP did not see any deviations from the standard model. This would not be so easy to do for strongly coupled new physics. And to my mind, supersymmetry is a theory which can be sensibly extrapolated to very high scales. There are many review articles, there are even books now for people who want to read. So I'll do some propaganda for supersymmetry now. In the third lecture, I will have a slide which is anti-propaganda for supersymmetry, what the problems with supersymmetry still are, in my view. Okay? So at one time, this instability of the Higgs sector was the only reason for new physics, which I take to be supersymmetry for now, at the weak scale. There were other motivations for new physics, but that didn't tell us what the scale was. And in supersymmetry, the 3-gauge couplings, in fact, which I said did not unify in the standard model, the measured values are just about right to approximately unify to a good precision if there is the simplest supersymmetric model that we take. Okay? And in order for that unification to happen, the superpartners have to be at a TeV, give or take, 1 order of magnitude. In supersymmetry, we'll see there is a symmetry which we call R parity, which is required for to stabilize the proton. That is part of my anti-propaganda slide, that the proton would naturally be unstable in supersymmetry. And if you assume this R parity is there, it need not be the only way to stabilize the proton, but if you take R parity to be a way of stabilizing the proton, it gives you a natural candidate for dark matter in standard Big Bang cosmology. Okay? And that again, these 3 arguments all suggest that superpartners should be at the weak scale, at the TeV scale. And that's a remarkable coincidence and has led to many discussions of supersymmetry over 30 or 35 years. I don't know whether there is a similar idea in physics, particle physics at least, which has lasted this long without any direct experimental evidence for it. Historically, I asked my senior colleagues and we couldn't think of anything. So whether we are doing the right thing or whether we are being just dragged along, I don't know. So, okay. So since we are talking about supersymmetry, let's talk about symmetries in a very basic manner. So examples of symmetries are translations, rotations, boosts, or isospin invariants, or local symmetries would be Yang-Mills or Maxwell gauge invariants. All these things have a generator of supersymmetry, as we all know from quantum mechanics, or a charge in a generalized sense. So for example, for translation, this generator would be the momentum operator. For rotations, it would be the angular momentum operator, and so on. And the fact that it is a supersymmetry means that that particular charge commutes with the Hamiltonian. And so if we have any state, eigenstate of the Hamiltonian with eigenvalue E, then Q state, since HQ is equal to QH, Q acting on the state, if it is not 0, it is a new state with the same eigenvalue E. So that's why we say that any symmetry implies degeneracies. And that's true for any symmetry. If we have rotational invariants, all the magnetic quantum numbers of the hydrogen atom, the hydrogen atom has the same eigenvalue, the same energy level. So it's the same idea which can be used for supersymmetry. And so if Q is a supercharge, and as we'll see that the state has to be a new state because Q carries angular momentum, we'll see that. But in general, if Q state gives you a new state, then that new state must have the same energy eigenvalue. And this is what we actually said. So there is a degeneracy in the spectrum. So let's consider now, instead of this general thing, let's make a SUSY toy model. So let's consider a theory with 2 spin-zero fields, real spin-zero fields, A and B. So there are 2 polarization states, right? One for A, one for B. And let's add to this theory a fermion, a Majorana fermion, whose antiparticle is itself. A Dirac fermion has 4 polarization states because it has 2 for the electron, 2 for the positron. But if the positron were the same as the electron, it would have only 2 states. So this is a theory with A and B, 2 spin-zero polarization states, and 2 fermionic polarization states for the Majorana fermion psi. And we'll anticipate that these obtain from some sort of a symmetry, and so they have a common mass m. So if we just wrote down the free Lagrangian, this is what we would write. The ordinary Lagrangian for A with a mass m, for B with a mass m, and for psi with a mass m. So this is very boring, there are no interactions. But notice that the bosonic degrees of freedom, two polarization state matches the fermionic polarization states. Anyway, let's now put in some interactions. The interactions, let's say, will distinguish A from B, because otherwise what distinguishes A and B? So let's say that A is a scalar and B is a pseudoscalar. In that case, the only interactions, renormalizable interactions we can write are A psi bar psi, this conserves parity, or B, because it is pseudoscalar, couples to the psi bar gamma 5 psi. And I is for hermiticity of the interaction. And similarly, we can write A cube terms because A has even parity, but we cannot write B cube terms because B cube term B would violate parity. B cube would violate parity conservation. So the things that conserve parity for a pseudoscalar B are these things. And so the most general interaction I could write would be this, except here I haven't written the most general interaction. I have put only one coupling constant G everywhere. In general, I could have written different couplings. This would suggest the reason that I've written one coupling constant is because we'll see that all the couplings are related by a symmetry. But this symmetry has to be a funny symmetry because it relates the couplings between scalars to couplings between fermions. Whereas almost all other symmetries that we knew only related couplings of fermions to fermions or bosons to bosons. We never had a symmetry which related couplings of fermions to bosons. Okay? If you just think of ordinary symmetries that we know, for example, isospin, it relates the couplings of pi plus, pi minus, pi zero. All of them are bosons, but it doesn't relate the coupling of pi plus to the coupling of a nucleon. Okay? So in that sense, this symmetry is very different. And this is why we call it supersymmetry. And technically, the charge of a SUSY is a fermionic charge, the generator of SUSY, Q SUSY. And so when Q SUSY acts on a bosonic state, it must give a fermionic state because Q itself carries some fermionness. If that is the case, then obviously this Q SUSY on the boson can never be an eigenstate or with the eigenstate of Q SUSY, right? Nothing can be an eigenstate of Q SUSY unless the eigenvalue is 0. Okay? And so this thing tells you that from our previous discussion we said that any symmetry will have the states, the new state and the old state having the same energy eigenvalue. So here also, as long as Q SUSY on a state is not 0, then the energy eigenvalue of the boson and fermion must be the same. But of course in the rest frame of the system, the energy is just a mass. And therefore, if supersymmetry is there, then for every fermion of a certain mass, there must be a boson with the same mass and vice versa. Okay? So this is very important. So, and these mass degenerate bosons and fermions will be called superpartners of each other. So, what are the properties of superpartners? Their masses are the same, and because Q SUSY was fermionic, the spins of the superpartners must differ by half. So, if we have Q SUSY acting on an electron, the superpartner of the electron should have spin 0 or spin 1. It can only differ by half. Now, spin 1 particles, the only way we know how to write them, at least I know how to write them, is if they are gauge particles. The electron has nothing to do with gauge invariance, and so in actual realizations, the superpartner of the electron will have spin 0. All other quantum numbers, like the gauge quantum numbers, the charge, the color, everything, Q SUSY commutes with the other quantum numbers. So that says that the superpartner and the particle must have the same value of other quantum numbers.
I didn't understand why not the spin 1.
Oh, because the only spin 1 particles, the only way I know how to write spin 1 things are gauge particles. And the electron doesn't have anything to do with being a gauge particle, right? It's not a watertight argument, but if the electron doesn't have anything to do with being a gauge boson. So probably the superpartner should have nothing to do with being a gauge boson. So there, from that point of view, spin 0 is. So this says, since all the partners' quantum numbers are the same, it means we automatically know all the gauge interactions of the superpartners because we know of ordinary particles. We know the gauge interactions of ordinary particles. If the superpartners have the same gauge quantum numbers, then we know all their gauge interactions. And this is what gives supersymmetry considerable predictive power. So now let me try to quickly tell you why these lambda square terms, the quadratic, so-called quadratic divergences, which were there for a generic standard model Higgs, are not there for scalars in the supersymmetric theory. So let's go back to that Lagrangian that we had. Oh, here. So notice the interactions. So I'm going to consider the tadpoles of A. So notice the A psi bar psi coupling has a G over root 2. The AB square coupling is here and here. If you take the difference, it's again GM over root 2, right? Just subtracting this from this, combining. And the A cubed interactions also has G over root 2 times the M. So let's look at the tadpoles. So the tadpole of A can go to psi bar psi. This is obviously quadratically divergent. A can go with a B loop, that is quadratically divergent, and A can go with an A loop. This is quadratically divergent. This had a coupling G over root 2, which I have factored out, not written down. This guy had a coupling GM over root 2, so the G over root 2 I have factored out, so I have written the M. And this guy had G over root 2, also GM over root 2, I factored out the G over root 2, but since there is an A cube term, I can choose any of the three A's in the A cube term to be the external guy. That can be done in three ways out of the A cubed. So that gets an extra factor 3. And this is naively what you would write down for the quadratic divergences if you're just using basic field theory. And if you evaluate this, you find that this is, if all the masses were the same, because all the masses are the same, this is obviously 0, if all the masses were the same. But it's also 0 even if the propagator masses MA, MB, and M psi are different. It's not exactly 0, but there is no lambda square term. You can actually see that. But what is very important is that M in the Lagrangian should be the same as the fermion mass. But the A mass and B mass could be different from the fermion mass, and still there is no quadratic divergence. Okay? So what is crucial is M should be equal to M psi, and that there was a common coupling G in order for the quadratic divergence to cancel. These terms are also other examples of lambda square terms in this theory, and I will leave it as an exercise for you to check, or we can check it offline if anybody wants to, together, that the lambda square terms again cancel irrespective of whether MA and MB are equal to M psi. So this is what I just told you, that lambda square term cancel as long as MA equal to M psi, and we have a common coupling G, but MA and MB need not be the same as M. The tadpoles are, okay, this is a technical comment. I have shown this to you only at one loop. What is true as this cancellation occurs to all orders in perturbation theory. Okay, that I'm not going to try to tell you, but just tell it to you as a fact. And the third point, which is important for model building, is that we must remember always that exact supersymmetry would have said MA and MB also have to be equal to M psi. But we said in order for this to cancel, the cancellation of the lambda square terms doesn't need that. So we can introduce terms, arbitrary terms for MA and MB. Even if there were arbitrary terms, this cancellation would occur. And if the cancellation occurs, we are happy. That was one of our motivations for stabilizing the Higgs mass, the scalar mass. So these terms like MA and MB, which are different from their from their symmetry values, will be said to break the symmetry softly. So we can, these soft symmetry breaking terms will play a critical role in our models. So now I'll give you a recipe for stabilizing the standard model. So first, we write down its supersymmetric extension. That will, for any symmetry to make a model which is symmetric, we have to extend the multiplet to be a realization of that symmetry, right? So for example, if we had isospin and I had only the proton, I have to put the neutron into the theory. So same way, I have to make a multiplet with all the superpartners for every standard model particle. Then the couplings are all related by the symmetry, the dimensionless couplings. That was like saying there was only one G before. And that will be enough to make the cancellation of these lambda square things that we didn't want. But this theory would be excluded by data. For example, there is no there is no spin zero particle with a mass of half MeV which has charge E. We know that from the data. But that doesn't matter because we could have given the boson partner a big mass and the lambda square terms would still cancel. We could give it a mass different from Me, as we just said. So supersymmetry cannot be exact, but that's okay. And so what sort of supersymmetry breaking terms we can allow? They are terms, the terms we allow are terms which don't bring back the lambda square terms. Okay? And so we can put in a big mass for the bosonic partner of the electron. Such terms will be called soft supersymmetry breaking terms. I will show you a list of them later. And these terms, these terms are crucial for model building in particle physics. If we can understand supersymmetry breaking, which we don't today, we will understand how these terms arise. And the only thing we have to take care of is the superpartners are heavy enough that we haven't seen them at accelerators today. If we can succeed in doing that, we would be okay. And because the cancellations are not complete, as I told you that what would happen if the standard model is coupled to now in this case with supersymmetry, then the correction to the Higgs mass, the lambda square would get replaced by the boson superpartner mass of the thing. It always comes in this combination because if the boson mass and fermion mass are the same, we must get 0. Okay? And these, so this lambda square term, log lambda term, I will not talk about. Optimally, we would like to break supersymmetry spontaneously. We don't have time to talk about that in these lectures, but for those of you who already know it, I'm just reminding you that there is something called the auxiliary field in the supermultiplet, and that should get a web. If you don't know about it, don't worry, it is not very critical for these lectures. So, okay. So how do we construct supersymmetry theories? We construct them in much the same way as we would construct, say, an isospin invariant theory. So for isospin, what would you do? You will make a complete multiplet, say a nucleon multiplet and pion multiplet. And then you know how these multiplets transform under isospin. You have the isospin calculus, and you will make an isospin invariant Lagrangian. I'm hoping everybody has seen something like this. You do this for any symmetry. For rotation invariants, we do the same thing. We make a multiplet of rotations, the rotation generators, and write down rotationally invariant terms. So we do the same thing for supersymmetry. So for that, the supermultiplets I denote with a hat. And this is called the superfield. It's called the chiral superfield. It has a scalar part, a Majorana fermion part, and this auxiliary component F, which I talked about. I just mentioned. It's not very critical. And because it is a multiplet, under supersymmetry, you can check the supersymmetry calculus. Under that, supersymmetry transforms these components into themselves. That's what we mean by a multiplet, right? And this F is called auxiliary because it doesn't have a kinetic energy term. So when we solve the equations of motion, the Euler-Lagrange equations for motions for F, these are just algebraic equations. So F, when you solve Euler-Lagrange equations, will be just a function of the scalars. Okay? Take that as a fact. Then, just as in isospin, we wrote down isospin invariant interactions with the isospin calculus. There is a superfield calculus, which I don't have time to tell you about. It's not difficult to write down SUSY invariant interactions. Okay? I won't tell you the details of the calculus, but I'll give you an answer by which you can construct your own SUSY theories. So we introduced a chiral multiplet, S hat. So let's say there are a bunch of chiral multiplets, S hat 1, S hat 2, S hat 3. Okay, so a bunch of scalar fields, scalar superfields. Then in ordinary field theory, if we had a bunch of scalar fields, we choose a scalar potential, which is a function of the fields. Same way, here we choose something called the superpotential, which is a function of the superfields. Okay? Once you choose that, this superpotential, just as we make the scalar potential invariant under all other symmetries, like Lorentz invariance or isospin invariance, gauge invariance, whatever, we must make the superpotential invariant under all the other symmetries that we want. Okay, that's just like ordinary field theory, except that we are doing it with the superfield calculus. And so that's what I said here. The only thing you must remember is this superpotential is only a function of the fields. It cannot be a function of a field and its adjoint. If it were, that would break supersymmetry. So this goes under a very fancy name of saying that F should be holomorphic. All that it means, it should be an analytic function. It should not be a function of S and S dagger both. Then what you can show is if these were chiral superfields, F is also a chiral superfield. And the F term of any chiral superfield, in particular of this F, it will be a function of all these things, will be a supersymmetric thing. It is automatically supersymmetric. That can be shown. That's part of the superfield calculus. So since you have taken a complicated function of many things, the F term, the auxiliary term of that thing, is a complicated function of all the scalars, but it is guaranteed to be supersymmetric. Okay? So that's the basic idea. And if you do that procedure, then the Lagrangian that you get is this thing, where F is the superpotential, then these are the scalar fields in the superpotential. So this is the usual kinetic energy term for scalars. This is the kinetic energy term for the Majorana fermions. And these blue and red terms are interaction terms. This is what gives us the scalar potential, because it is just taking the derivative of F with respect to the scalar fields and setting all the fields to be their scalars, scalar values. So this is just a function of all the scalar components. So this is exactly what we will call as the scalar potential in ordinary field theory. And these are the interactions between the fermions and the scalars. Okay? So this thing will give you the most general thing that you can write down. You choose your F and you can write down the corresponding supersymmetric theory. This Lagrangian is guaranteed to be supersymmetric. You can easily check that renormalizability means that F should be at most cubic in S, and you can also check that if you choose this superpotential and write S equal to, decompose this complex field S as A plus IB, you get back the toy model that we started with, which I showed you earlier. For gauge theories, we do the similar thing. SUSY supersymmetric gauge theories. We have to introduce, of course, we have to include the gauge bosons, which have two polarizations each. So to match the polarizations, I have superpartners which are called gauginos, which are Majorana fields, which also have two polarizations, so degrees of freedom match. And then their multiplet is the supermultiplet of the gauge supermultiplet contains the gauge boson, the gaugino, and its auxiliary field, just as we had an auxiliary field here. And if you do that, then it's a little more work, but not difficult, but straightforward. The most general thing that you can get, the Lagrangian, is this. These first line is just the kinetic energy terms that you are familiar with for fermions and gauge bosons. This is the Yukawa interaction, this is the interaction between the matter fermion, the thing in the chiral multiplet, its superpartner, and the gaugino. It's the analog of the electron-electron-photon interaction. This is the term which gives the scalar potential along with this, which we had, and this term we already had. I mean, I'm just throwing this formula out, don't worry about it, but this is a recipe book. If you followed this recipe, you would be able to write the most general supersymmetric gauge theory. I'm sorry I don't have time to discuss this in detail, and there were a bunch of covariant derivatives here, which I wrote down in the next. These are just the gauge covariant derivatives. So with that, how much time do I have left? Okay. So with that, we are ready to construct the supersymmetric version of the standard model. So if you look at the standard model, the fields that we have in the standard model are here: a doublet of leptons, a singlet. We usually write it as a right-handed electron, but we could have written it instead as a left-handed positron, which is a singlet. Same thing for the quarks. We usually write UR and DR, but instead I could have written it like this. And then the quantum numbers are given here, and then we have a Higgs doublet. Okay, these are and with that, so if you go to a standard model restaurant, this will be the thing on the menu. If you go to a supersymmetric restaurant, it will be exactly the same thing, except you will put superfields. So you will have a doublet of leptons, you will have the singlet electron superfield, same for the quark superfields as we had. The only thing you will have, and for the reasons we'll see, is there will be two Higgs boson doublets. Okay, and these are the quantum numbers. So once you know that quantum numbers, you can go to that most general Lagrangian that I had written down and write down the interactions, provided you knew the superpotential. I haven't told you what the superpotential still is. But let's make some, what the heck did I write here? Oh yeah, so here I told you I had to write everything in terms of left chiral superfields because you couldn't, so take that as part of supersymmetry. That's why we wrote it as left-handed positron rather than right-handed singlet electron. The two Higgs field doublets actually have mirrored quantum numbers if you go back to that table under the gauge group. Okay? And we'll see that that is exactly what we need. And why we need two, I'll tell you. In addition, there were superpartners of the gauge bosons, the gauginos. Those superpartners have the same quantum numbers as the gauge boson. So the superpartner of the gluon is called the gluino. It has spin half, but it must be color octet, and SU2 cross U1 singlet. And likewise for the gauge bosons of the W and the B in the standard model. So if we knew the superpotential, we would be able to write the most general supersymmetric theory, and we have to add soft SUSY breaking terms. So the superpotential that we choose is, these are, if you didn't have supersymmetry, this is exact, oh well, you won't write a superpotential, but you can check that these terms, the red terms and the green terms, are exactly what you would write, which will give you the Yukawa interactions in the standard model of the fermions. But you have to write them in a supersymmetric way. Okay? I mean, I'm not explaining this, you have to do some work to check that. Plug this superpotential into our formula that we had, that general formula, and you will get the usual Yukawa interactions of the standard model. The extra term I had to write was this blue term. It's called the mu term. This gives mass to the Higgs bosons, Higgs multiplet. So you can check that this is 3-to-1 invariant, and that with the superpotential, you see that the down quark, right-handed down quark, or the singlet down quark, couples to HD. So this vacuum expectation value will give mass to the down quark. This guy gives mass to the up quarks. And the HD also gives mass to the leptons. So down-type fermions get mass from the vacuum expectation value of HD. The up-type fermions will get mass from the vacuum expectation value of HU. Now, why did we need two? In the standard model, to get mass, one was enough. But in the standard model, we were allowed to use phi and phi dagger. There was no restriction. But I told you that in supersymmetry, you cannot use phi dagger in the superpotential. That's why you had to invent a new multiplet which had exactly the same quantum numbers as phi dagger. That was HD. Okay, I call phi as HU, then the other guy is HD. Okay, so that's why we needed 2. The fact that these were mirror quantum numbers is great, because when we introduce new fermions, you would get what are called anomalies, which destroy the consistency of gauge theories. But if the other guy, so there would be anomalies they only come from fermions. So now in this Higgs multiplet, we have extra fermions. That would make the theory anomalous. But because we have the other doublet with the opposite quantum numbers, the anomaly from HU type fermions exactly cancels automatically the anomaly from HD type fermions. And that theory is consistent. So a recap of the particle content of this theory is called the minimal supersymmetric standard model. So these are the ordinary matter particles that we knew. In supersymmetry, we have all the superpartners. Now, of course, and here we have 2 Higgs fields and the corresponding Higgsino. So there are 4 complex fields here, 8 real fields, right? 3 of those fields get eaten up by the Higgs mechanism to give masses to the W and Z, and we are left with 5 physical fields. 2 of those physical fields combine to make a complex field, charged Higgs, and the other 3 guys are neutral Higgs fields. So in supersymmetry, we have 3 neutral Higgs bosons and a charged Higgs boson pair. These guys, the gauginos, the photino, the vino, and the xeno have spin half, and these are SU2, a joint SU2, spin 1, the vector, the gauge partners, but the gauge symmetry is broken, and once the gauge symmetry is broken, this isospin 1 and the isospin half Higginos can mix, and they combine to give us a pair of Chargino pairs and neutralino pairs. So there are 2 Dirac Charginos after mixing and 4 Majorana neutralinos. Again, offline we can discuss this counting. So all these partners on the right hand side are predicted by the symmetry. But what we have done, you say you have invented so many partners, but what we are really doing is we have invented a symmetry and we are just completing the symmetry multiplet. This is exactly what Dirac did way back when he invented the positron. In that case, this symmetry was charge conjugation, or when omega minus was invented to complete the SU3 multiplet for old people of the 60s. So completing a multiplet, of course, brings new particles in, a multiplet of symmetry. So the real postulate is the symmetry, not that you invented all these new particles. This is what I told you about. The running gauge couplings, these are the inverses, do not seem to unify. These are the measured values at LEP, do not seem to unify in the standard model. But in the supersymmetric version of the standard model with 2 Higgs doublets, they seem to unify reasonably well. If we had made 4 Higgs doublets, again, they would not unify. So I don't know whether this is a malicious act on part of nature or real. So if we take this model that we have just described and add all the so-called soft supersymmetry breaking terms, which I have listed for you here, we get what is called as the minimal supersymmetric standard model. Okay? It is the minimal extension of the standard model that will be consistent with phenomenology. The soft terms that we can add are scalar masses. They are like the MA and MB that we talked about. The gaugino mass terms are also soft. And it turns out these bilinear and trilinear scalar interactions are also soft. And since the symmetry is broken, in principle, we could add terms which are have a dagger in them. Okay? These are usually not included by many people, but logically I think they are there. And at least for the standard model, because these would give you tadpoles, but since there are no singlets, gauge singlets in the standard model, there are no tadpoles, so this is okay for those of you who know. Otherwise, don't worry about that remark. Okay. So here I have to make another confession, and that is part of the anti-propaganda slide. We could have added this list of terms to the superpotential. Don't pay attention to them. You can go and check they are gauge invariant and renormalizable. But these they also violate baryon or lepton number conservation, which means a generic supersymmetric theory should have baryon and lepton number violation. We don't want that. And this would be big, because this is renormalizable lepton and baryon number violation. But in supersymmetry, if we set this to be 0 to start with, it would not be regenerated by radiative correction. Supersymmetry protects these terms. Okay, so technically it is okay, but we need an explanation for this. And that's one of the anti-propaganda things for supersymmetry. We can exclude these terms by defining something called matter parity, which is equivalent to what is called R parity. R parity is given by this. This is the baryon number, this is the lepton number, and this is the spin. You can again go and check for our MSSM multiplets. These are equivalent, and that for R parity, the standard model particles will be all even under R, and the superpartners, the new particles that we invented, will be odd under R. So if R parity is conserved, this is called R parity. If R parity is conserved, and if we don't write this superpotential terms, the symmetry, the theory we get will respect R parity. I want to emphasize that it is perfectly possible to write down sensible R parity violating models, but I won't discuss them here. What are the implications of R parity conservation? One is it will save proton from decaying. If we wrote generic R parity violating terms, the proton would decay at the order with weak interactions, lifetimes, and none of us would be here. So that would be a bad thing. Okay? And N-bar oscillations would be there, again, because baryon number would be violated, but they have not been seen, so that would have been a bad thing. These R parity violating terms forbids any mixing between leptons and the neutralinos. Both are spin half particles, and those with the same electric charge after SU2 cross U1 breaking would be able to mix. But R parity forbids them because leptons are R even and these guys are R odd. Superpartners can, if R parity is good and we only have R even states in our initial state, we have protons and electrons and so on, we bang them together, we must produce an R even state at the end, which means superpartners can only be pair produced in accelerators. You cannot produce a single superpartner by itself if R parity is conserved. And from the point of view of this conference, this is very important that the lightest supersymmetric particle has to be stable because it is the lightest R odd particle. If R is conserved, it cannot decay only into standard model particles because the initial state is R minus 1. If the final state had only standard model particles, it would be R even, and odd cannot decay to even. And so this guy would be stable. And if this lightest guy happened to be electrically and colored neutral, it would have no strong interactions, no weak interactions, it would not emit light, there would be no charges, and it would look like dark matter, which is the subject of this workshop, if it existed, of course. And a last remark is heavy superparticles, when they decay, that decay must end, in the lightest supersymmetric particle, right, by definition, because that is the last R even particle, R out particle. Okay, so we talked about, since this is a dark matter meeting, I must pretend to say something about dark matter. So these stable lightest supersymmetric particles, as the universe was cooling, there would have been all sorts of things. They would have been in thermal equilibrium to start with. But as the universe cools, these would freeze out. What that means is initially when the universe was hot, annihilations were producing dark matter, reactions were producing dark matter particles at equal rates as dark matter particles were disappearing into ordinary particles. That is thermal equilibrium. But when the universe becomes cold enough, when the temperature of the universe becomes of the order of the dark matter mass, the forward reaction of producing dark matter particles is suppressed kinematically, because the initial particles have energies which are too small to produce dark matter particles. Okay? And so the reaction rates would become imbalanced. It would go out of thermal equilibrium. And ultimately, as it expands, the dark matter particles would dilute only with respect to the expansion of the universe as 1 over a cubed, not Boltzmann, a being the scale factor of the universe, the size of the universe, because that number would not be changing. They can't find one another to annihilate. Okay? So that's called freeze out. And actually it doesn't happen at the dark matter mass because of the Boltzmann tail. It happens at a slightly colder temperature, typically an order of magnitude colder. So we can, assuming thermal equilibrium, we can calculate their abundance now. And this actually, the measured value, gives stringent constraints. As we said, this dark matter, the lightest supersymmetric particle, if it were electrically charged or colored, it would bind with ordinary particles to make funny isotopes. Okay? So suppose the dark matter particle were colored, it would make nucleus with its mass, which is way heavier than ordinary nuclear masses. Or if it were charged, it would make exotic hydrogen with an electron replaced by that charged dark matter particle. And searches for these say that, so we can calculate their abundance. Their abundance is expected at this level, but experimental limits are orders of magnitude below. In fact, this 10 raised to minus 28 for hydrogen is an amazing number to me. One of my colleagues, former colleagues, was on this experiment and I talked to him about it. It was interesting how they got such numbers. So there are good arguments to suggest from these experimental arguments that dark matter particles are not charged or colored. I mean, the lightest supersymmetric particle cannot be charged or colored because it would make funny isotopes which we haven't seen. And so it must be electrically and colored neutral. Within the standard model, the supersymmetric MSSM that we have discussed, if you look at that menu, the only possibilities are a neutralino or the partner of the neutrino. The partner of the neutrino is not favored experimentally because neutrinos interact with the Z. That's a big coupling, right? It's a full strength gauge coupling. And if these guys were there, scalar neutrinos were the dark matter, super K would have seen signals long ago from the sun, from annihilation of scalar neutrinos via the Z into neutrinos. So very high energy neutrinos. High energy means their masses would be of the order of this neutrino mass. So these are extremely high energies compared to nuclear physics processes in the sun. And so these have been excluded quite stringently, way back when. These limits can be evaded by using clever tricks, but we won't talk about that. So today, in the MSSM at least, most people consider the neutralino as the most viable dark matter candidate. In local supersymmetry, if you make supersymmetry a local symmetry, that has to do with gravity, because supersymmetry, I didn't talk about it, is the anti-commutator of two supersymmetric charges is a translation. It has a space-time thing. So gravity comes in that way. And the partner of the graviton is also electrically neutral. It could be a dark matter candidate. If, as at these lectures, we are going to discuss the axion, if you put the axion in a supersymmetric theory, the axion is part of a supersymmetric multiplet, and there are things, superpartners called axinos. They are also electrically neutral, and they could be dark matter, part of the dark matter. And I think Pierre will talk, I don't know whether you will talk about that or not, yeah. I emphasize there is absolutely no reason that I know of that all the dark matter should compose of a single particle. That's a prejudice that we have. It's called simplicity, but it's still a prejudice. Even the visible matter that we see has several particles, is composed of several particles. And there is much more dark matter by mass than visible particles. And yeah, so it all hinged upon this R parity conservation. And yeah, in supersymmetry. And just as we had R parity in supersymmetry, the other extensions that I had alluded to, either using extra dimensions and compactifying extra dimensions, in that case there would be, the new particles would be Kaluza-Klein excitations. And there is a similar symmetry called Kaluza-Klein parity, which makes a new particle in that sector, it can be even or odd, the lightest particle with odd Kaluza-Klein parity is also stable. In these models where I said you postpone the problem, they are called little Higgs models, there is something called T parity, which makes the lightest T odd particle stable. So there is a parallel with these different extensions as in supersymmetry. And most of the phenomenology that I'm going to do, I will do it for supersymmetry, but you will see that there are, because of this T parity or KK parity, there are analogies. Particles have to be produced in pairs, the lightest guy is stable, and so on, even though we won't realize these. So, since we said that superparticles which were produced always decay into the stable LSP, which is electrically and colored neutral, so it doesn't have strong interactions, it doesn't have electromagnetic interactions. Our experimental colleagues at colliders haven't gotten smart enough to build colliders, build detectors which will see a neutrino, the energy deposit of a neutrino, because it's teensy or doesn't happen very often. Same way, the LSP, because it doesn't have stronger electromagnetic interactions, almost deposits no energy in the detector. So they can't see it. It escapes, but they don't know it escapes, just as a neutrino would escape. So it looks like, so what they would see is, if they could measure the full energy and momentum, they would see an apparent energy momentum non-conservation because of escaping particles. This is a generic signal for all these type of new physics which have a stable particle, be it KK particles or this little Higgs particles or supersymmetric particles. Generically, because of this conserved parity, there will be missing energy in these events. Okay. So this might be yeah, so maybe I'll stop with this one and then we can take questions. So I didn't emphasize it, but if you had counted parameters or if you had been awake, you would have seen that the generic MSSM had 178 parameters, and they were parameters because we didn't know how supersymmetry was broken. So we just parametrized it consistent with all the other symmetries that we knew. And so many of my friends kind of piss on me when I say, hey, you're working in a model with 178 parameters, you can fit a horse with it. And isn't that terrible? But I want to emphasize that most of these parameters occur in the SUSY breaking sector. And we don't understand anything about SUSY breaking. And for people who are old enough, I imagine, I'm not old enough for that, and probably nobody in the room is old enough, but it would be like the situation for weak interactions before V minus A. Every weak interaction of a particle, hadronic decay, say a sigma, you would have these 16 operators, the 16 quartic, 4 Fermi interactions, and a different one for every particle. You would have had a shit pile of parameters. And you would have said, this is a terrible theory. But once we understood how that weak interactions were part of a gauge symmetry and how the gauge symmetry is broken, all these huge number of parameters simply collapsed into what we call the standard model today. And we call that a great success, which it is. And so my prejudice is that if we understand SUSY breaking, then SUSY will become a very nice predictive theory. That all this ugliness of SUSY, and there is an immense amount of it, is all in the SUSY breaking sector, which we have no idea. Okay, so here I've talked about, the bottom part of the slide I won't discuss. The last remark I will make here is we assumed R parity as though we pulled it out of our hat, which we did. we were forced to, but there are models one can make with higher gauge symmetries in which the conservation of R parity appears more automatic. So maybe I should stop here, and tomorrow we will hopefully continue with models of SUSY breaking. So I welcome any questions, and if these lectures are too low or too high, please give me feedback and I can try to adjust. So thank you very much.
Any questions?
What about the left-right symmetry? Is there any interesting feature introduced by left-right symmetry, since you are using that there is a big symmetry, high energy?
Well, what I did here was supersymmetrized the standard model, which was not left-right symmetric. If you wanted, if you are a fan of left-right symmetry, you can take a left-right symmetric model and supersymmetrize it. You can supersymmetrize a left-right symmetric model, right? So then you would have a much richer or many more particles. So all the WRs will have a gaugino of WR and so on. I don't know whether anybody has examined this in any great detail.
But at some point you would expect that they should also recover that.
Yeah, so if you are a fan of left-right symmetry, you should expect that. Yeah.
More questions?
Well, if you allow the electronic, the electron player violation or violating part in the
R parity.
R parity, then you first of all you will avoid this missing energy.
Yes.
And besides that, you can explain the light neutrino masses, right?
Yeah. So I myself long ago have written things, and many authors have written things on making models of neutrino mass, which come from exactly what you're saying. The business of avoiding missing energy, you don't completely avoid it, because we'll see next time that often, so suppose you're producing gluinos, and heavy gluinos tend to cascade decay down. If they cascade decay down, these cascade decays contain neutrinos, not LSPs. And you get, if you do it for these lepton number violating R parity interactions, you get a lot of leptons. So actually the reach of a collider increases because of all these leptons. So you get multiple leptons, which you don't get in the standard model, along with modest missing energy. And the reach actually increases. The bad way of doing this, if you don't use leptonic R parity violating interactions, but if you use hadronic ones, then there can be problems. But even for those models, so I don't know, maybe 15, 20 years ago in SNOMAS we tried to study, can we hide supersymmetry by this thing? And we tried very hard to hide it. And so normally when you say that SUSY could be brought to, say, in those days we used to say 1.5 TeV or something gluino, with R parity violating, baryon number violating interactions, we could still see SUSY up to about 1 TeV. This is with 10 inverse femtomile longer. So it reduced the reach, but not immensely. Because of cascade decays, you could use leptons, and you didn't need missing energy as much. So, I don't know modern studies. I don't remember. Yeah.
This is about the same question that was asked before. You mentioned gaugino, so why didn't you construct partners of fermions with vectors?
So, as I said, I don't have a fantastically good argument. The only thing I said was, so if you try to construct, I have not tried to do this, but this is, so I'm telling you my prejudice. If you try to do it, you will have to have new gauge bosons. Okay? One argument is you haven't seen this. But second is somehow the electron, the part whose partner is the gauge boson, so this gauge boson would carry lepton number, and so somehow the electron would have something to do with this gauge symmetry. And maybe I don't have enough imagination, but at least I couldn't see it. And so from that point of view, I'm saying certainly it is correct to say it is much simpler or much more straightforward to construct it with scalars. I'm not quoting this as a theorem. Yeah, obviously not. maybe somebody has a better argument and I would learn.
More questions? There are no more questions. Let's thank Professor Tata again and move on to the next
Thank you.
lecture.
So I'm going to try without this. Yeah. If I talk like this, can you hear me fine? Because I'd rather not use the microphone, and I'm used to talking to a lot of students. Is that okay?
Está transmitiendo, tiene que poner, si no, no escucha la transmisión.
We're on link, sorry. Okay, are you recording? Yes. Is that the problem? Okay. Yeah. So I don't have, just a second. Oh. Is there a way to, so here? Very hard keys. Okay, here you are, you can do that. I need the other, I'll show you. Oh no. Have my own.
Our next speaker, you ready?
Hopefully we're ready. Can you hear me all right on this then? Okay.
Is Professor Priscilla Cushman from Minnesota, which will talk about WIMP direct detection.
All right, thank you. So I've got 3 lectures, and the first one is basically the current state of the technology. So we'll talk about the experiments, the targets, and the limits. The lecture 2 is that low mass WIMPs have become interesting, so wanted to explain sort of why that is. Perhaps it's our disenchantment with Susie, and our new techniques, and finally we'll talk about backgrounds. So yeah, there we are. So this is, I just have a few slides to introduce some of what actually Xerxes talked about right at the last couple of slides, which is, of course, there's tons of candidates that we can think of, but we do prefer particles that simultaneously solve another problem. And so this is why we tend to concentrate on these SUSY relics, for example. There's glucocline modes as well, which are actually also WIMPs, and then axions, which you'll hear about because they restore the CP symmetry in QCD. Of course, whatever particle we want to invent has to not violate astrophysical observables, for example, the diffuse gamma ray background, also these exotic kinds of matter that you would get if you had something which had color and charge. So then we ask ourselves, what particle can do all of that, but also match the observed relic density starting from thermodynamic equilibrium in the early universe? And those are particles with annihilation cross-sections at the weak scale, or what we call weakly interacting massive particles. And then this is actually also something which was just mentioned, but I wanted to define when people talk about the WIMP miracle, which it's perhaps just a coincidence, so we have to make sure that we keep that in mind. But it is a clue that dark matter might interact with the weak force, even though it doesn't with the others. And so you have dark matter particles annihilating via the weak force when they encounter their antiparticles. But then as the universe expands and cools, you have this freeze out. So here, whoops, here you have the basically the Boltzmann suppression occurring, and then at some point when the particles and their antiparticles are too far apart to even find each other to do the annihilation, you have what's called freeze out. And depending on the interaction, whether they're annihilating more strongly or less strongly, that defines when freeze-out occurs, or how much are left when freeze-out occurs. And it turns out that the measured relic density implies the cross-section required for that is the weak scale. And that's what that coincidence or that WIMP miracle is what leads us to concentrate on these WIMPs. But I think it is important for one to put up this anti-hubris plot at some point. There's just an enormous amount of space here, parameter space between mass and cross-section that you can conceive of things. And we're talking about this little small section here when we talk about weak interaction acting particles. In fact, if you like, this is the region that we will be probing over the next decade, and of that we've gotten this far. So when you see a plot like this, which has all of our, this is a little out of date, but our limits for the experiments that exist now, and this thing which I'll mention later, which is how far we can go with these before we begin to run into an irreducible background, where this is a very definable problem. We have parameter space to explore, and that's what we're doing. So we're talking about direct detection of WIMPs. That means a terrestrial experiment in which we actually see a WIMP interact with a target material here on Earth. They have both particle physics and astrophysics. So looking up at the particle physics part here, we're talking about some sort of an interaction. And we're talking about a simple elastic scattering experiment, basically. If it is a neutralino, there would be some exchange of Higgs or Xenos or a Z and the squark. So here's the cross section. We generally parameterize this in two forms: spin dependent and spin dependent. So if it's spin independent interaction, we're talking about a coherent scatter with a whole nucleus. And so this is great because there is an enhancement of A squared. The other way we talk about it is the spin dependent. For that, if you have a target, you've got protons and neutron spins basically canceling each other out, except for what else is left over, that unpaired nucleon. And if you have a target with spin, you can place limits on an interaction assumed to be spin dependent. You have to deal with astrophysics, and we'll have a talk later on that too. If you see it, this is supposed to be a sort of WIMP halo, I guess. In any case, you have some WIMP distribution in our galaxy, and we make an assumption that it's basically this isothermal spherical halo with a Maxwell-Boltzmann velocity distribution. We have some parameters that we can talk about this. We know how fast we're moving through this cloud of WIMPs. And we know also if we have a density, we have an escape velocity for those, if the WIMPs are going too fast, which I don't know, yeah, here we go. We can only integrate across the distribution up till when they have already left our halo, if you like. And so all of this is the sort of standard way we parameterize what we're looking for. I want to therefore say a caveat before we go any further. We clearly know our halo is not have a Maxwell-Boltzmann distribution. We know it has cusps and structure. We know that there are things like the Sagittarius, this collision that happened eons ago that has left a material behind. And but we choose a standard halo model. That's what I talked about before. That's the standard halo model. We also don't know the interaction, which, so we use the simplest scattering assumptions, and those are the two pieces of the particle physics I said. It has a practical advantage because we need some assumptions to start designing our detector. And we also need to be able to compare results across different targets and technologies. So we continue with this thing, which we know is somewhat of a fiction, but it's very useful. If you look at, for example, back at this equation, well, I don't know if you can see it, and I'm not doing a lot of physics of justifying this because I want to get to the technologies, but basically you get some sort of a sort of quasi-exponential recoil spectrum. It is exponential for these massive dark matter masses, but much less than your target mass. But what that ends up being is it says that you've got energies that you're depositing in your detectors, which are very, very small, which means you need very sensitive detectors. And the rate, which you can also calculate using these assumptions, means that you're going to see only a few events per year in enormous ton-scale detectors, so you need very low backgrounds. The details, of course, of this spectrum depend on the nuclear physics of the target material itself. More specifically, things you have, here's three target materials, argon, germanium, and xenon that we use a lot, and their atomic mass. And not only that, but you have a form factor in here too. I mean, how large basically is that nucleus in the Fourier transform of its edge, if you like. And so if you take the form factor times the rest of what you've got here, you've got a differential rate, which varies for each target. And so even, for example, xenon, which starts up higher here because of its form factor, has basically, its form factor only goes up to 100. If I were to have drawn, could have done another picture where you would actually see something that looks more like a form factor, meaning you have this xenon's coming down to its first bump in its, the transform of its width. In any case, so what do you do with this? How do you detect these? There are really three different ways we have. One is that we just count these nuclear recoils. This is elastic scattering. We're just going to count each scatter that we see. Or we can take advantage of the fact that as the Earth-Sun system moves around the galaxy, sometimes the Earth is basically moving in the direction of this relative WIMP wind and sometimes moving opposite to it. So there should be an annual variation in the flux, or at least in the, it's not so much in the flux, but in the kinetic energy of the WIMP wind. And you can also look at the direction of this WIMP wind between, as a daily modulation. Now, if you try to count nuclear recoils, you have to, you have one big advantage, which is you could actually identify each of the WIMPs. This would not be a statistical measurement as it would be down here. You'd be actually saying there went a WIMP, and then this is a background. But of course, to do that, you need to really reduce your background quite a bit as well. And you need to identify what most of the background is. Now, most of the background are electron recoils. So if you have a light particle, like a gamma or an electron, then when it comes and to your atom, it will tend to recoil off the electron, which then zooms through the material, shedding lots of electron hole pairs as it goes. So there's a lot of ionization that way, for example. Whereas for a nuclear recoil, basically I think of it as the nucleus just kind of going thud when it gets hit by. So you have a way of telling the difference between these two. And so I'll talk a little bit about how people do that. The other nuclear recoil that can happen, of course, is another neutral particle, the neutron, and that also produces a nuclear recoil. So basically, we just try to shield those. However, in this case, when you're counting, whether it is or not, if there's something that looks just like a WIMP, And neutrinos can coherently scatter, and generally the cross-section is so low we haven't worried about it. But it does create an irreducible background at some point. So anyway, annual flux variation. This is just a 3% variation in the amplitude expected, depending, of course, on the threshold of your device and a number of other considerations we'll talk about later. And you get data, you get a lot of different characteristic things you can look at, the shape, the period, the amplitude, the phase. But you do need a lot of detailed systematic studies to avoid competing effects that can also happen annually. I mean, you can imagine that temperature, there's a lot of things that vary on a yearly basis. This is directional modulation as a large modulation in the anisotropy, meaning if you can know the direction, it does a really good job. For this, you would use a tracker. But normally trackers, and I'll talk more about this later, have less, are like made of gas tracker or something, which means your targets have to get huge. We'll talk about this one first. So I want to try it, which is probably going to be really difficult. That's why I'm kind of racing along here, because I'd like to go through these three different techniques. So counting nuclear recoils. Here are the types of signals we have to use. We can use heat or vibration, charge or light. And here's the targets that produce any of these. We have scintillators of various types. Most objects, if you put a voltage across, you can ionize them, so that would be charge. And then there's a number of cryogenic techniques. So let's put them together, and what are the experiments that actually use these various signals. And you can see that some of them use just one form of signal, and some here use a combination. So these would be ionization and scintillation. Before I go on, I'm going to come back to that in a moment, but if we're talking about counting nuclear recoils, we're going to need to talk about the background on an event-by-event basis. And so I did mention this already. The neutrons, we do have some statistical handles on getting rid of neutrons. They tend to multiply scatter because their mean free path through our target is small enough that you'll get several scatters. And it also, if you have multiple targets, the cross-section of the interaction with the neutrons varies with target. So it's one of the reasons in CDMS originally we had both silicon and germanium, because we assumed that we would be seeing both WIMPs and neutrons, and that we would then be able to look at the difference in how many there were in each. Eventually, just to finish that statement, we ended up going with germanium a lot because germanium is heavier and we could get up to bigger exposure sooner. And interestingly enough, now we're going back to both silicon and germanium because we're now looking at low mass WIMPs. So this whole study of direct detection has gone through a lot of changes in focus as time goes on, and as we begin to probe deeper and deeper, and we need larger and larger installations. The other thing is to go deep. Of course, just get rid of the neutrons. So that's why they're all underground experiments. And we also have shielding with layers of hydrogenous material to get rid of the neutrons, and then high Z material to get rid of the gammas, and then more hydrogenous material to get rid of the neutrons that the high Z material created a sea of more thermal like neutrons. I will talk about actually shielding in my third talk. And then for electron recoil background, we need to discriminate between these two recoils. We can either find a way to discriminate by the technology itself, or we can use self-shielding because the backgrounds are usually coming from the outside, or we can eliminate the sensitivity to electron recoils altogether, and those are threshold devices. Or, in fact, we can simply model the background and subtract it. But now we're no longer having event-by-event particle identification. Now we're saying on a statistical basis, what an excess of nuclear recoils above our model background is. So it's a little different. It's not a background-free experiment anymore. Alpha particles, I didn't say much. They're actually easily identified by most of the technologies because of the higher energy deposition, but they have been a problem for threshold devices and trackers, and we'll talk about that on the third lecture. So here's the picture. I wanted to start with the original explorers, and those are basically high purity germanium, which started out as a hunt for double beta decay, neutrinoless double beta decay, and has morphed for many of them into a search for dark matter. High purity germanium detectors have a band gap, only 0.7 eV. They operate at liquid nitrogen temperatures. They're very compact, high density, and they were originally optimized for a neutrinoless double beta decay. And for those ones, you would enrich it in an even nucleus. Either way, though, you end up with a beautiful energy resolution and very low noise, which means they're equally good whether or not you're looking for an endpoint here, or whether you're looking here for some difference in this well-known spectrum that could be due to the WIMPs. Now what's happened is that high purity germanium has had a makeover, and there have been a lot of new advances. This is the conventional design here, which of course we still use extensively for isotope screening. And these are HPGE. If I use that terminology later on, that's what you know I'm talking about. And you see that there's a P plus basically electrode in here. And when you have a particle interaction, say here and here, then the charge is collected in two different places. You get a sort of smear because it has to be collected out on this P plus. The new technology is called a P-type point contact. So you see that now you've got things brought to a small contact. Of course, being that it's a small contact, it has low capacitance. And so these give you sub-keV thresholds and improved resolution and the ability to see multiple interactions and do pulse shape discrimination. So that's the type of thing that Cogent uses. And Cogent is one of the experiments. And of course, anything that's good for this low mass dark matter detector with this great energy resolution is also a good neutrino detector, and it's still a good double beta decay. So this technology is used for lots of them, and this is just in order for you to see. These are all of these cosmogenic peaks and how good a job this energy resolution can do at understanding the background. And if you understand the background very well, then you can make a claim that there is an additional signal on top of the background which might be due to WIMPs. And so this is from an older Cogent publication, but I rather like it because I like the way that you can see here is a model for what a 7 JeV WIMP or a 10 JeV WIMP would be, and they had an excess. And so that would have been their signal for having possibly seen WIMPs, WIMP dark matter. There are other players in this game as well. One of the major ones is Texono, and they basically were making a lot of these new ultra-low, high-purity germanium detectors, ultra-sensitive ones, for magnetic moments, neutrino, coherent scattering. And so recently they've combined with CDEX at the, or they have become CDEX with other people, and they moved one of their devices at the new Jinping lab in China very deep in order to actually do a scattering experiment. I mean, a low mass WIMP dark matter experiment. So underground labs, this is, I'm going to keep repeating this. You're going to see a picture of something about the technology and then where it is. So you have Cogent over here at Sudan and Texono and CDEX here. All right, so that was one. They only use they use energy resolution. If you want to exploit a media, you want something with a different response to nuclear recoil and electron recoil, you can go to a two-channel strategy. So you have one signal, one either scintillation or charge or something which has a difference in response to nuclear recoils and electron recoils, and a second signal which basically normalizes the energy scale. And so the first of these two-channel strategies I'm going to talk about are CREST, CDMS, and Edelweiss. So they are all phonon or bolometric experiments, and one of them uses a second channel of scintillation and the other uses a second channel of ionization. Basically, compared to liquid nitrogen, we're talking about very cryogenic detectors. So these are running at like 50 millikelvin or less. And taking advantage of the fact that if you want to be sensitive to a very small energy deposition and specific heat goes as T cubed, then being cold is very useful. And when you get so cold, you are actually have no need for doping your detector. You're actually sort of depleted already. You have efficient charge collection at very low drift fields. So it's important, people probably don't realize, when I say low drift fields, I'm talking about applying voltages of 3 or 4 volts across a device in order to collect the ionization. I have to move ahead. Some of this stuff I'll talk in more detail in the next two. So there's two kinds of heat signal. One that's a true heat signal, a bolometric one, and that's Edelweiss. They actually use an NTD sensor, which they plop on top of their big hunk of germanium. Whereas CREST and CDMS are looking at athermal phonons, and both of them actually use transition edge sensors. But for CDMS, it's thousands of these tiny tungsten transition edge sensors that are put on by photolithography, and on CREST there is an evaporated thin tungsten film on it. The difference is basically that CREST has to run at a very low temperature, between 8 and 10 millikelvin, and CDMS runs more like, well, actually that's an old slide, but 50 to 70 millikelvin. And of course what you have is you're moving between being superconducting and normal, and so a very small deposition of energy will cause a very large change in the basically feedback current that you see as the resistance changes. And so this is how we can get very, very sensitive thermometers, really. And the readout, therefore, has to be through squid. So here's a picture, a kind of summary of it. These are the old experiments, CDMS2, Edelweiss, and CREST2. And you'll see that the phonon, the left and are here and here, and the bolometric in the middle. And CDMS Edelweiss's second signal is ionization. So we apply a voltage across the crystal and read out the drifted charge. And CREST has scintillation, and CREST is kind of clever because it's the calcium tungstate crystal under here has both light and phonon. The phonons, you can see, okay, you have TES here, and you read it out with a squid. But in fact, you also read out the light through a squid. And so basically the light from the calcium tungstate is captured by the sapphire, which then creates the phonons that are read out by the same squid array. So it's kind of a clever technology. In the end, in order to distinguish between nuclear recoils and electron recoils, everyone uses this thing which we call yield, and there are other ways of doing it, but it's basically the ratio between your two signals, either charge to phonon, charge to heat, or light to phonon. And so what you have is, and these are of course pictures of the basically neutrons from a californium source, or photons from, say, a barium source, or I'm not sure whether they use the same source, but so this band here is the place where all of your background is. This is where your electron recoils are congregating, whereas in this band is where your nuclear recoils are congregating. And you can talk about the fact that this band has been quenched, which just tells you that you have a smaller ionization signal here by a factor of 3 than you do for the electron recoils. And for both Edelweiss and CDMS, it's the same factor of 3. However, CREST, because we're talking about calcium tungstate, we've got the tungsten part of it, we've got the oxygen part of it, all of them are very well separated. So that comes to our second problem, which is you'll notice that there are there are these extra confusing pieces that droop down into the nuclear recoil band, and that comes from basically incomplete charge collection, which happens near the surfaces of these. So if they don't collect all the ionization, then that ratio of ionization to phonon is low, too low, and in fact can come down and droop into the band where your signal is. So this is your proxy for where you want the WIMPs. This is where your background does, and you get a separation. And sorry? This? So those are signals. Those are gamma lines, basically, so that's why they're concentrated like that. Okay. So what happens is that when I've oversimplified things when it makes you think that there must be a grid like this, right? And so that if you have a gamma line, it must just go like this. But in fact, when I'm talking about recoil energy here, you're talking about a trade-off as this thing deposits the energy in the crystal. I'll talk a lot about this in 2 lectures, but let me introduce the idea right now that there is a bit of a problem when you take an electron hole pair in a crystal and you put a voltage across it, then that starts to move the electron hole pairs through the crystal. Well, when they do that, they shed phonons because it is a crystal. There is an interaction with the lattice. And then what that does is it introduces additional phonons that come down into that recoil energy. So there is, in the denominator, is something that depends a bit on the electron recoil there. Now, because all right, so that's the answer to that question. Can't remember what I was going to say next. I think I've answered your question, though. There was some other point. Well, I'll come to it if I think of it. So anyway, we have to get rid of this, right? Because this obviously does not give you excellent discrimination. These guys don't have to worry about it because they've got such a large quenching factor. We have a smaller quenching factor, and we have to deal with that, and we've dealt with it in many different ways over the years. The way we do it now is we actually mold the field itself in such a way that a bulk event, this is actually an Edelweiss picture. They apply electrodes of 4 volts, which are your drifting electrodes, but they also have interleaved electrodes at minus 1.5 and plus 1.5. This means that any interaction that's near the surface gets pulled off to the side. And then you can tell the difference between a surface event and a non-surface event. We have to be a little more careful because remember they have this. The phonons are just detected by an NTT detector stuck on their surface. We're detecting it by lots and lots of electrodes, all photolithography on our surface, and so we have to interleave our electrodes with our phonon signals, and this is how it's done. If you look at any one of these small blue dots, it's actually our TES in the middle, our aluminum fins, and grounding that moves around. Either way, we also shape our field so that we can make a symmetry cut. And anything that's on the edges, we can recognize. Anything in the bulk, we don't. So that actually completely gets rid of this. It does bring up a point that all of these small modular detectors also have fiducial cuts, but compared to liquid xenon, where your fiducial cut is basically all the self-shielding stuff around it, and then you get to look at the inner bit, we have to do our fiducialization module by module. And it's done by this field shaping. So this is the CDMS field shaping. It's slightly different. Anything on the surface gets pulled to the other electrodes and we don't see it. And so we basically cut out all that. We cut the side surfaces also because we have a veto electrode. So anything that comes on the side, actually, these electrodes know that it happened here and get rid of it. So vertical fiducialization and sidewall fiducialization. Edelweiss, fully, this is FID, that's fully interleaved detector, I think. Because you can see that they actually have all those little electrode lines all on the sides as well, instead of just an electrode. Anyway, there's tons of technology. I'm realizing I could just go on forever, and I'm really sorry. And so already spending too much time on this. Edelweiss 3, with this 800, almost 900 gram germanium bolometers, and here's their little heat sensor there. And their results that you'll be seeing, any limits, were from a run that went from 2014 to 2015. They are now busy. They had some additional backgrounds they're trying to understand. They're doing R&D on it, and they will have a new run in 2017. Our run at Sudan ended in December last year, and we are preparing a new experiment for Snow Lab, which will start in 2020. Part of what we're doing there is building an enormous cryostat and refrigerator system, and we're working with Edelweiss, and it's very, once we've run our first small payload, we will be putting Edelweiss detectors in as well. So the two collaborations are joining forces at that stage. CREST has also made improvements. They've had 18 modules running since 2013, and the most recent results are coming from one module. So it's one crystal of calcium tungstate that is really low background. And here you see a few more details. You see this basic yield band structure, right? But now there's a bit more detail. You can see that the yield band for oxygen is somewhat different than the yield band from tungsten. And they basically make a threshold cut, and this is the acceptance region where they look for WIMPs. CREST 3 is not yet taking data, and it's going to look very different from CREST 2, and I'll talk about that in my next lecture. In general, these solid-state detectors are much more sensitive. They have very good discrimination between electron recoils and nuclear recoils, but they're generally harder to scale up, and so all of their limits tend to be on this side of the plot, and all of our thrust for the future is to move in this direction to look for the lower and lower mass WIMPs because there's plenty of space here to bring the limits down, whereas the liquid noble gases are concentrating in this region at the higher WIMP mass. And the underground labs with this cryogenic solid state are CREST and Edelweiss in Europe, and CDMS2 moving to Snow Lab as Super CDMS.
So what's the restriction for the size of the crystal? That's usually got from simulations and
the size of the crystal is practical one of growing a crystal that large.
That's what sets the...
Practically, that's really it. Plus, we use all of this solid-state technology that is used in industry. Mm-hmm. And so the size, even for the ones who were putting at Snow Lab, we had to get special equipment in order to do polishing so large and in order to do the photolithography on a larger surface area. So it's mostly that. There's no real, it's just the growing of the crystals. And once you get larger crystals also, there's nobody else doing that. So when you talk to industry, you have to be the only ones who are prompting them to do it. So, it ends up being difficult to, it becomes expensive. And that's what makes it expensive, is that there's no mass production of these already happening for detector grade crystals in the world, but what we do. We also have scintillation to ionization, and these are the dual phase noble liquids, for example. So we're still talking 2 channels. You can use argon or xenon. This is just a quick table of the difference between them. Obviously, xenon gives you a larger A-squared coherent enhancement, so you can get to larger exposures quicker, but and also an easier wavelength region to work in. This is very ultraviolet for argon. Argon's cheaper though, and argon though only has even nuclei, so if you want to go for a spin-dependent limit, you do better with xenon. They both have problems with removing a bulk contaminant. It's argon-39 and krypton-85 for xenon, but both of these have been basically solved. Distillation works for krypton-85, and for argon, they've found new underground argon that is very low in argon-39, and that has made the argon possible, really. Dual phase noble liquids are TPCs, basically. The incoming particle scatters in the liquid xenon and produces scintillation light and electron hole pairs. There's a field which drifts the electrons up to the surface, where there is actually the electrons then convert to light. So there is an additional scintillation signal, but it's really the electron signal, but it's called S2. This is a TPC, so you get vertical position information from time of flight of these, basically, and position information from in X and Y by arrays of photodetectors. And the difference for electron recoils versus nuclear recoils is given by the amount of S2 versus the amount of S1. So S1 and S2 will be your yield at this point, and you can see a little picture here. Now, what happens with that yield is not as good. Remember, those yield plots that you got before for electron recoil and nuclear recoil were well well separated, but we had to work a little harder for those on fiducial cuts for the surface events. Here, they're very close to each other, but they have the self-shielding and fiducial cuts, and all of the background ends up on the sides. So that's how they make up for that. There's just tons of these experiments. So this is a summary. The Xenon 1 ton is now running, and Zeppelin is finished, and Lux is actually finished. And Lux and Zeppelin together is what LZ stands for. So these two have now proposed and been approved for the next large experiment at the Sanford lab. Panda X is coming up fast, and it's a running experiment now. Under liquid argon, you also have dual phase experiments. This one, WARP, is actually had problems with its high voltage, so it's no longer running, and it's considered basically it was a study for the future ones, such as the argon dark matter, which is running in Confranc, and dark side, which is running at LNGS. And now I have a bunch of pictures, but no time to go over them, but they all look pretty much the same. Panda X produced some very nice results, so I thought I would show their results here just so those two pictures that I showed for the technology, you can see exactly what happens. This is from IDM 2016. Here's their fiducial cut, and in that fiducial cut, there was only one candidate event. This is what their ER versus NR looks like, and again, they have to do, cuts, 99% acceptance, but you see this band now has all gone away because of those fiducial cuts, and there's their one candidate. And so Lux's final result is shown here. Xenon 100 is now running 1 ton, so this is the result they presented in 2016 for data that was taken a couple years ago. And then Panda X is still running, and this is where they are already, so they're hot on the trail. The Panda X is probably, since these guys they're the one to look for next, and Xenon 1 ton. And Lux is going to have to wait till LZ. And notice they're all here in the higher WIMP mass range. Two-phase argon is just gearing up. It has an advantage in that it has two component scintillation. It's got a 6 nanosecond and a slow microsecond scintillation component. And so here you can see that a neutron tends to have very fast signal, whereas the background has slower. So there, instead of yield, argon uses something called F90, which is the fraction of S1 light detected in the first 90 nanoseconds of the pulse. Please notice that S1, S2 in argon has now been relegated to additional discrimination. So this is no longer, the pulse shape advantage in argon is so great that that's what, for example, dark side 50 uses as its initial separation band. So your band is F90. Here is your background, or where your right is your background, which is then cut quite a bit again by S2, S1 in a radial cut. And then those are just pictures. We have dark side and ARDM. Moving right along, the next piece we have is the scintillation only for noble liquids. So we haven't gotten out of noble liquids here. These are all noble liquids. See them all? But here's been talking about two phases, dual phase, two different channels that we're using to beat down the nuclear recoil versus electron recoil. Here, we're talking about single phase. Why would you do that when you have such a good advantage with two phases? Well, it's simple, right? It's basically they all look like this with a bunch of PMTs around them. They're easy to scale up to enormous exposures, and because they don't have some of that discrimination, it's more important in them to remove all the bulk contaminants you possibly can. And position information is needed to make a very nice fiducial cut. In liquid xenon, I think I've mentioned some of these before. Liquid argon, of course, has the advantage of this pulse shape, and it relaxes the fiducial cut requirement. And these are the three. X-mass is the xenon one. Deep is running now, and that's at Snow Lab. That's the argon one. I'm not sure if you might know what Clean's status is these days, but Clean has had its problems, but I put it up here for completeness in any case. However, I think Deep is the one to look for a new result. When are you going to?
Deep was built last week, so it's now on dark matter.
It's not Deep 3600 anymore?
Yep.
Right, oh, I just didn't write that. Here it is. Anyway, I think that this I included as your advertisement as to why there is a niche for these single-phase noble liquids. Here are your xenon curves, right? And you notice what they look like compared to what Deep 3600 can do. And you can see that we have a problem here at the lower masses. You have a high threshold, and then that's really a function pretty much of the fact that you don't have the discrimination. On the other hand, you can get down quite low here, and here's the theoretical advertisement, which is, we don't have to abandon supersymmetry quite yet. Maybe it's just harder and heavier, and everything's just a little bit more difficult. We still should look in this region, and if, for example, this were where the contour was, Deep would be poised to be able to make that measurement. Right, so you can read this, but I think there is a case for that. And so here's all, this will be, I assume my slides will be there and you can look at them. I've tried to color code everything. So we start with our single phase, and the xenon is white and the argon is this black, and they're pink because they're single phase. And then you have the double phase, Lux, xenon, Panda X, and that's where they're all Those are the ones that are basically to look for now. And there's, of course, new ones that have been proposed. I think I just go on.
Do you know about xenon? Already?
Xenon 1 ton?
Yeah.
Yeah, I mean, they seem to be running. They seem to be. What do you mean? Do I know? Do they have a result? No.
No, they are not testing anymore. They are not.
No, I thought they were running. I thought they started running about a month ago. Does anyone know more?
In 3 months, they should have. They should be close to locked, right? Or not
One thing I don't know is whether they're going to do a blind analysis or not. So a blind analysis is always something that takes a whole lot longer. And in fact, Lux did not do a traditional blind analysis. They actually salted their data. So they put fake data in instead of blinding the area so that they could watch for new backgrounds that might come in that otherwise you'd be blind to being able to see. So then on this side, we do have another just scintillation, which are the inorganic crystals, sodium iodide and cesium iodide. Of course, DAMA, the famous annual modulation experiment, uses sodium iodide. Kim's actually did an experiment where they did not see annual modulation, but they used cesium iodide. I really don't have time to go through all of these, but I want to show you a picture of their cesium iodide array, and there are advantages to cesium iodide, and this is one of the reasons it's called Kim's. It's got another name too, but I'm sure they made it up afterwards, which is Korea Invisible Mass Search. In any case, there are advantages of cesium iodide, but if in the end you want to compare directly to DAMA, you probably want to use the same crystals, and that's why they're moving to a sodium iodide array, and they're using their cesium iodide as basically a shield. And they're going to, the new name of what they're doing is called cosine 100. And they're doing that with DMICE, which I haven't mentioned, but was an experiment at the South Pole with only a few sodium iodide detectors. And they're going to Kim's low threshold, and it looks a lot like CREST. So what they're doing is they're exploring various scintillators instead of the calcium tungstate that CREST has. And here's all of the different kinds they're looking at. Right, I thought I'd said that. Anyway, they do have some data already on a molybdenum. It's not exactly this crystal. So they're up and coming too, and they want to corner the market on low threshold devices. And finally, sometimes one signal is enough. Can also be applied to a simple heat experiment. And these are the threshold detectors. This is the original set of 3 experiments, which I just put up here in order to remind you that one of the first types of experiments used dosimeter technology, actually. So they had a suspension of superheated droplets. These are all various kinds of fluorocarbons. Here we have droplets in a water-based gel and piezoelectric transducers. And then Ku started up at Fermilab with actual bubble chambers. But Picasso and Ku joined forces, and so we now have a SNOLAB program of increasing sizes in various fluorocarbon targets, which is called PICO. So it was basically a combination, a lot of the personnel and acoustic transducers from Picasso with the Ku bubble chamber technology. And here's a picture of the 2-liter detector. There are multiple readout signals. There's stereo vision with cameras, acoustic transducers. Neutrons, of course, this is a picture of a neutron because you see 2 bubbles, so you see a multiple scatter. And so a multiple scatter, since 60% of the neutrons actually make multiple bubbles, they can be removed with a reconstructed image from the cameras. And then the gamma and beta is just removed because the threshold, the pressure and temperature are arranged in such a way that electron recoils don't make bubbles. Of course, you need to, this is great once you decide on your particular material that you're going to use. But if you want to go to low thresholds, of course, the lower the threshold, the more possibility there is that you'll get the bubbles for the electron recall. So there's a trade-off there you need to work on. The WIMP search region for pico is actually, could be, one way to do it is to just write the acoustic pressure versus the number of counts. Because what you're looking at here, the acoustic pressure is how you tell the difference between say an alpha and a neutron. So if you just look at an americium beryllium source, right? So here you have your neutrons, and it's hard to see black versus red here. I don't know, maybe you can. This is black here. So these are the alphas that come from the radon. This is the neutrons. So that now you can set where your limits, your WIMP search limits are going to be. And then when you run the actual dark matter search, you can cut out all these alphas. And there's one event here. There's one event here. So here you have your, in a sense, a fiducial cut as well, done by camera, if you like. And this was one of the latest results. You'll notice there's a spin-independent result, but now the one that's bigger, the one that you advertise, is a spin-dependent one. And that's because of the fluorine. So here you have the pico 2L run. This is the most recent, right? Yeah, okay. And it's beginning to come down to the point where it can compete with some of the neutrino experiments that look for neutrinos from WIMP annihilation in the sun. I know I'm going over, well, actually not so badly because I started so late. Okay, maybe I am racing through this quicker enough. I wanted to give you the overview. It's very frustrating because I want to tell you more detail, and each time I say, no, I have to go on because I want to get through the picture. I want you to see the big picture. Now, because I started talking about Cu, and because when I talked earlier about cesium iodide and sodium iodide, we didn't really talk very much about the spin-dependent cross-section, so let's do that now. We can parameterize basically the cross-section of a spin-dependent cross-section in terms of the actual unpaired spin and the expectation value that you have. That's what the SP protons. Now this is parameterized with respect to proton coupling and neutron coupling. So in other words, you have to invent a parameterization, sort of, and then you analyze in that context, and then you can set limits for coupling to protons or coupling to neutrons. Of course, this could also have been rewritten in terms of the basis vectors of isoscalar and isovector coupling as well, and sometimes you'll see that. But if you just talk about what your target looks like, let's say for proton coupling, the materials that are going to give you good limits on that are ones that have a high expectation value with respect to the proton coupling itself, but also how big J is. So how big is the spin, the unpaired spin anyway. So you see iodine, sodium, and cesium are pretty good here, and aluminum. So that puts the CREST experiment and these crystal experiments in the proton coupling category. Under neutron coupling, xenon has, I think xenon has like 8 isotopes. So it's got lots of isotopes naturally occurring. And of those, 26% is xenon 129 and 21% xenon 131, both of which have unpaired neutrons. Germanium 73 also does, but there's only 7.73% of it in our germanium naturally occurring. You can enrich it, and if you're going to do a dedicated spin-dependent cross-section experiment, you could consider doing that. And then you would have a better sensitivity to that. And silicon also has a little bit of odd N. Oh, and then fluorine's the champ, and that's why all of these experiments are using fluorocarbons, and we have coupling 0.441 there, and a J equals 1/2 for fluorine. All right, and the other thing I wanted to point out with respect to spin-dependent couplings is that it's really important to have many targets. And here we've got another plane in which to talk about the coupling. This is the coupling to protons and the coupling to neutrons in 2 dimensions. And you can see, I had to do this because I'm not sure you could see it, but here you have the sodium iodide, cesium iodide. These are actually big, long ellipses like this. So what we're narrowing down, and we're looking at the region in which things are accepted. And you can see that these lines are basically restricting it in the coupling to protons. And here's fluorine, and then xenon, which is mostly restricting it in terms of neutron coupling. Now the reason I put this on here, this very complicated plot, is, and this is an old example, but I rather like it, when the simple experiment did its final spin-dependent limits. Let's see if I can, so simple is here. So in the fluorine one that I've got the red lines here, and the purple are the limits for simple. Now because simple's limits could then be restricted because of the tilt due to xenon's limits, creating this one small place. So if you look at the limits in proton from simple, these are the limits that it used, not this one and this one. And so it needed xenon 10's results to achieve the limit that it wrote here. And I think it's just one example of the ways in which we have to be very careful not to say there's one technology that's the best and we should do everything with that, because they really do complement each other in very specific ways. The last few things I want to say are that we won't keep looking for WIMPs forever. Actually, that's a lie. But we say this to the funding agencies because there is a point at which it becomes very hard. And it becomes hard because we have a neutrino spectrum that's reaching the Earth from various sources. So what you see over here are various spectra. You have the PP chain from the sun. We have CNO chain here, but split up. But here's the CNO chain. This is almost too complicated a plot. Sometimes you see a simpler one. But these are solar neutrinos. And then we have down here in yellow, we have a diffuse source from all the supernova core collapses that are happening all around in any other supernova stuff that's happening and it's reaching the Earth with neutrinos. And then we have the atmospheric neutrinos produced basically by cosmic rays in our atmosphere. And so this creates coherent neutrino scattering, which is basically a nuclear recoil. And so once you get down to that sensitivities, we have things that start to look like the same thing as the WIMPs. So to explain what this plot is, this, first of all, is now the event rate in our detector. And this particular one is for germanium, and it's the recoil energy. So the blue dotted line is what our germanium detector would see, the number of events per ton year, per keV, and the energy. Now, what these red lines are models for what the WIMP-only spectrum should look like. So if we didn't know that we had these neutrinos, we'd see this signal from the neutrinos, and we'd model it as a WIMP. And you can see that some of these models look almost identical. They match the spectrum. So if you want to try to translate this into where the spectrum of your irreducible background, you do lots and lots of simulated coherent neutrino scattering experiments, and you make fits for various thresholds for them. And you also say, well, what threshold, what exposure gives me what WIMP mass? And when you do that, you get this line. So this line is, above this line, you can have an experiment with a 90% probability to get the 3 sigma detection of a WIMP. Below that, as you get down below this line, you're getting confused. So we call that the neutrino floor. And the G2, this is generation 2, so the US funding agency has decided that it wants to get to the neutrino floor. And the way it plans to do that is to use, it chose 2 generation 2 experiments, one of which was LZ to cover this area, and one of which is super CDMS to cover this area. And you'll see that super CDMS has lots of different lines here, and those details I'll go over with you in a later lecture. And it has to do with various kinds of detectors, silicon or germanium, high voltage, phonon only, that we plan to use. So to go below the neutrino floor, though, you need modulation experiments. At some point, you can't just keep counting. You need to be able to see that there's more than what you expect from the solar neutrinos. And you need to have something that changes either with respect to the year or with respect to the direction, because, of course, the neutrinos that are one of your big backgrounds are either diffuse or coming from the sun, as opposed to coming in the direction of the WIMP wind, which is Cygnus. Which, by the way, I didn't put this on the slide, but I'll be talking about these directional experiments, and they've all gotten together under the name Cygnus, and that's the direction that we're all headed in terms of, that's the direction the WIMP wind is coming from, put it another way. It's a robust signature, daily direction modulation, and I think I made some comments. Compared to annual modulation, you can think of all sorts of background sources that change with from summer to winter, but because this is a sidereal rather than diurnal signal, it's much easier to get rid of backgrounds. Directionality is the key, so you want to be sensitive to the sense. You don't want to just see a track like this. You want to know, did it come from my fingers to here or from my shoulder down now? Right? That's the sense or the direction of it. An example is, I took this from DNT TPC. They are gas TPC directional experiments. And you can see that a WIMP scatter here would create a track, and you can observe the track with both photomultiplier tubes and a CCD in this particular realization of it. And then the EDX along this track gives the direction of it. There is a tension here. You need a low gas density to make those tracks long enough so you can see the direction and you can clearly see the difference between background and signal too. But you need a high gas density to get the best exposure. So I'm not sure that these are going to be the future. It may be that a lot of people are talking about high pressure TPCs and other things. A lot of R&D needs to be done for that. And this is just a list of the 4 that are doing active R&D and are actually, many of them underground, taking data right now. But their limits are not very competitive, of course, because they just don't have enough mass and they won't get enough events. And then I should make one comment about DAMA. This is the annual flux variation. This is a picture of the difference between what you see in June when you have basically a maximum. So say you have a threshold here, right? So you really can't see this. Then you basically are talking about more flux in June and less flux in December. You can see you need to be careful here, because if you get a really low value of the threshold here, what's really happening is a change in the kinetic energy. So it's not fixed that the phase max is always in June. The phase max could be, depending on how you actually do the experiment, in December. But for this particular experiment, we're talking about an amplitude of a few percent. We're talking about a significance of 9.3 sigma. We should never ignore 9.3 sigma. I mean, this annual modulation is very compelling. This is the integrated spectrum of the single hits. So here's some background, right? So what you can see is that this bump here is basically that which is giving the variation. The modulation amplitude, you can also do it as a function of energy, and the modulation that you see here is only significant at these low energies. So this is the amount, the amplitude of that modulation. So in a sense, this is a low mass WIMP, if it's a WIMP that they're looking at. But of course, so far, a standard WIMP hypothesis is not seen by any other experiment using other methods. So, and to make that point, I guess Cogent did. For a while it was 2.8 sigma, but they've now revised it down to 2.2 sigma, and personally, compared to DAMA, I don't find that particularly compelling. And Kim's, as I mentioned, they did cesium iodide, they did the same thing, and this is just a picture showing there would be an annual modulation on top of this. It was 2009 to 2011. We also looked for an annual modulation. We didn't see one, and Xenon 100 had a beautiful, last year you can read their paper, and they actually not only didn't see one, but their not seeing one was a 4.8 sigma exclusion of DAMA's signal. But it's always been a pain because there is nobody out there doing repeating DAMA's experiment. And the reason is because it's very hard. The reason originally was because DAMA made an exclusive contract with Saint-Gobain, and so they could not share how they made these pure crystals with anybody else. There had to be a whole new program of R&D starting from scratch to get crystals that were pure enough to compete with DAMA. But that has happened. And so now you've got a bunch of people who are at the verge of being able to begin experiments that will be conclusive evidence and to look for the DAMA oscillation. You have SABRE, which is 50 kilograms in Gran Sasso. So it's the same lab as DAMA. That's good. They'll study the backgrounds because they're in this huge liquid scintillator active shield. Basically, they're to test the Borexino test facility, which is excellent. So they're going to embed this in an incredibly active, very low background active shield. We've got a bunch of other labs, Aeneas, Picolon, and Cosine. So Cosine was the Kim's group. And Picolon and Aeneas. And then these are different labs in the northern hemisphere. The southern hemisphere is interesting because the southern hemisphere there is an annual modulation of something you can detect in a detector, and that's the muon flux. The muon flux has an annual variation, which depends on the basically temperatures and pressures in the upper atmosphere, and it's the same in the northern hemisphere. That annual modulation is roughly the same as the annual modulation sense that DAMA saw. So everyone's always said, is there some way that this is causing your effect? And in the southern hemisphere, the muon flux oscillates in an opposite sense to what you expect from the WIMPs. So that's very nice. DMICE has a few detectors down there, but this is very difficult to get IceCube to melt more holes for you when ice cubes finish, basically, and all. And they may put some more in there eventually, but they've teamed up with Kim's to make Cosine. SABRE has a South American arm in Australia, so they will be working with the Australians to also put another, hopefully 50 kilogram installation there. So I think, I think it's about 5 years from now we might see some information. Okay, that's all. So I tried to give you the big picture. There are just so many detector concepts, and I didn't cover them all. You have different technologies. When you have new territory, for example, low mass WIMPs, you get new unexplained backgrounds, and you need the checks and balances for the different technologies. You need to compare systematics and different locations. And any new signal, if you do see one in one technology, needs multiple confirmations before anyone's going to believe it. And the signals are not just going to jump out at you. I mean, we take these steps, these baby steps every time in sensitivity, so it is always going to be the fact that the first real signal that is seen will be one or two events. And then different targets, different sensitivities. I mean, that's going to be important when we even see WIMPs, which we will, when we see WIMPs, not if, I hope. Anyway, is it spin dependent? You want to learn the physics of the interaction. Is it spin dependent, or is it, or not? Or is it more complicated? I haven't talked at all about effective field theories, which open up the whole panoply of different kinds of nuclear physics interactions you could have. We can then begin to factor out astrophysical uncertainties and measure the WIMP mass, measure the cross-section, and maybe even do WIMP astronomy in some time in the future. Okay, thank you.
Do we have more questions for Prisca? Yeah.
So last year in PICO we published the CF3I data, and we mostly excluded the DAMA signal. So that's interesting because we also have iodine.
Yes, that's right. And there's, well, you could say more about, I mean, I didn't go in any detail about showing the contours for DAMA, but there's a contour for the target being sodium and a contour for the target being iodine. And so it doesn't have to be sodium iodine. I mean, you guys had the iodine in the what was your fluorocarbon? CF3I. Yeah. And there's actually other people who also, of course, looked at the DAMA signal. I mean, any simple nuclear counting experiment, of course, doesn't see stuff except for the few hints. I'll talk about all those hints in the third lecture, I think, or the second lecture. But
yes.
So, I mean, I have a question about the 9.3 sigma defined. Is that just saying that a flat distribution is ruled out by
correct.
9.3 sigma, or is the actual signal gives you a chi-square that is almost 90 units better than the first one?
Oh, it's the second, because
stronger, right?
Yes, it's very strong that, and let me say the points, that it is sinusoidal. So I mean, it's a model of what that
There's only two pre-parameters.
So. Right, the amplitude tells you how much, so that's not it, but it's the sinusoidalness of it, the phase, that's probably only the two, right? Yeah, but of course we don't know what's causing it.
So it's believed that it's there, it's just not clear what it is. Right?
Yeah, I mean, if there were no other, I mean, this is a good example, if there were no other experiments out there to say that we've looked for WIMPs in all these different ways, and for consistency, if we have this model, our experiment shows that we don't have this model. And you're using that model to claim that this oscillation is a WIMP. Those are inconsistent. And if those experiments didn't exist, I don't know how we would not find this proof. They often say it's a model-independent proof of dark matter, by which they say that, well, you know, over the last 10 years, they have gone through all these different models to show how there is a model that works for them and would not have worked for anyone else. In other words, all right, here's one that is really strained, but what if the dark matter is more dense in one place than in another, right? And they're, going through that. And nuclear counting experiments would not be able to tell that. They just look at an overall thing. So, I mean, that has been the argument, is how can we make a model that would agree with that, but not agree with the limits and exclusions of all the other experiments. And no one has been able to come up with a convincing way of talking about something that we would still call dark matter, and would satisfy all those constraints.
But what about the other experiments at Kansas? I mean, they are in the same place, right? Other experiments
Yeah.
for direct circuits at Kansas. Did they reach these regions of gamma already or not?
So no, the ones, the SABRE and all of those. Are you talking about other annual modulation experiments? No. No. Okay. Well, the other experiments are simply not seeing WIMPs with the kind of spectrum of energy deposition that you would expect. Is that what you're asking? I'm not sure I understand what you're asking. They're in Gran Sasso, right? But if there is a background that is changing with annual variation, then that could be this background, and those other experiments would not be looking at annual modulation. They wouldn't see that background. And the xenon experiment did look. Xenon is there, xenon 100. But they're just, and they didn't see the effect. So that's why I think the 4.8 sigma, the xenon 100 exclusion seems the most effective to me because it is at the same lab. So if there was, and they actually looked at annual modulation in their xenon, so whatever's causing that, they didn't see that. But I mean, no one has a good explanation for what background would cause this either. So I mean, it's not, this is hard. And to give, DAMA, to give them credit, they actually have done a lot of tests. This is only single scatters, not multiple scatters. They have all sorts of ways to measure the muon flux. I really don't think it's the muon flux because they have, it's also, muon flux isn't quite the same phase. So I don't think anyone knows what causes that. And that's why people go to the sodium iodide, because that just, okay, if it's a background, we don't know what it is, maybe it's a background that is specific to sodium iodide.
More questions?
Very nice question. Why was it placed in Grand Sasso as opposed to in the South Pole, Michigan? Or South Pole, actually in the Southern Hemisphere.
Why was SABRE not put in the South Pole?
Or in the Southern Hemisphere.
Oh, in the Southern Hemisphere, SABRE is doing something in Australia.
That is afterwards, right?
Yeah, it's just because what they're going for right now is this unknown background. They're going to use sodium iodide, but they're going to put it in the counting test facility, that CTF that they used to do the first screening for Borexino, which is a facility that can look for all those backgrounds. It will see what's coming in as well as what's in the sodium iodide. So it's this incredible active shield. Oh, well, then they'll try to figure out what's from. Because to see the signal in the liquid scintillator, they have this huge active shield that will look at all what's coming in, as opposed to DAMA, which has crystals with phototubes on the end in a copper and shield like that, but they don't have an active shield. So they'll see the cosmic rays, they'll see if there are additional, somehow neutrons. I don't know where they would come from, but what if there's an annual flux of neutrons from something? They'll see those. They'll actually be able to monitor the background at the same time. And so there's only that many purified sodium iodide crystals in the world anyway. So if there were plenty of them, you'd just put them both in the northern and southern hemisphere right away. But all these groups are working really hard to get enough of them to make large enough arrays so that they'll be competitive at some point. Does that answer your question?
I have a last question. All these experiments, are they specific for a range of masses, or could you detect, say, different kinds of dark matter if there were more than one kind, as Professor Tata was saying? Could you do that with one experiment, or you need that, or all of them are specific?
Depending on the technologies. For example, CDMS also looked for ALPS, so axion-like particles from the sun and galactic ones. So we looked for axions in the sun, but it was very specific to our technology. So, for example, we were looking at Bragg scattering. In the crystal would actually be able to convert back to gammas. And so our crystal, because it has very specific orientation and because it's carried around the Earth at various angles to the sun, you can do a likelihood calculation of the Bragg scattering angle enhancements as a function of day and season, and look over 2 years of running to find out whether you see the pattern you expect to see from axions streaming from the sun, so a particular location, and looking at it. And any crystal experiment any crystal experiment where you know how you put them in, and you know, which we didn't really well know because we didn't think about doing this before, and also has the crystal axes 111 or 101 placed in the right. So that would be one way. There's tons of others, I'm sure, but yeah, people could, but you usually design an experiment for the particular technology you're looking for. So our design is specific for, was originally for medium or high mass WIMPs. And we wanted to do that in order, the way we did that was we had a zero background experiment. We could get rid of every electron recoil and only have the nuclear recoils. Therefore, if we saw something, it was a candidate. Right? Now, our technology has changed because we were too expensive to make enough exposure, and the xenon experiments cornered that market. But our technology now is not a background-free experiment. We model our backgrounds, we put a high voltage on the detector, and we look for low mass WIMPs. In a sense, that is a different WIMP. So the technology has changed to look for a different kind of WIMP, which may not even be, so these might be supersymmetric WIMPs, these might be asymmetric dark matter. That's a different kind of dark matter, and maybe they both are there, actually. So, you know, maybe we're going to look for one kind of dark matter, and xenon's looking for another dark matter. So we're already looking for two different kinds of dark matter.
Well, if there are no more questions, we thank Priscilla again.
Thank you.
And we invite you to a nice coffee break out here.